Jai Hind everyone. I am Jyoti Sharma from Electrical and Electronics Department of AKGEC Engineering College. I am serving as Assistant Professor over there, and I will be taking certain lecture series on the topic transformer, that is unit 3 of the subject Basic Electrical Engineering of first year, and its code is KEE 101 according to AKTU. Now coming to the topic I am going to take, that is transformers. The series of the lectures, the very first lecture I am going to take, that will be having the contents: what is actually the definition of a transformer, what is its working principle, that is the principle on which the transformer works, then what is the construction it is having, then what are the various types of transformers based upon their classification, based upon their applications, based upon the working principle, then what is the EMF equation of the transformer, and what are the characteristics of an ideal transformer, how does that work. That will be the content for the lecture 1. Okay, going for the definition of the transformer, right. So, what is a transformer? A transformer is nothing but it is a static piece of device by means of which an electrical power is transferred from one electrical current circuit to the another electrical circuit. Basically, it transforms either the voltage level or the current level, keeping the frequency at both the sides constant, right. There is no electrical contact between the two sides, that means the two sides of the electrical circuits. The desired change in the voltage or the current is obtained without any change in the frequency. The working principle of the transformer, that is mutual induction, as it can be seen in the circuit as well. You know, this is the core of the transformer, this is the primary winding of the transformer which can be seen over here, this is the secondary winding of the transformer on the second limb. Then in that, when we give the primary voltage, how does we have the step up of the voltage or the step down of the voltage being occurring in the secondary side, that is being given by the mutual induction. Now, what is this working principle? What is this mutual induction is all about? So, the basic principle on which the transformer works is the Faraday's law of electromagnetic induction or mutual induction between the two coils. The working of the transformer can be explained as the principle of mutual induction that states that when the two coils are inductively coupled, and if the current in one coil changes uniformly, then the EMF is induced in the other coil. This EMF can drive a current when the closed path is provided to it, right. So, if we just see when the alternating current flows in the primary coil, a changing magnetic flux is generated around the primary coil. Because of that changing magnetic field that is being transferred to the secondary coil through the iron core. The changing magnetic flux is cut by the secondary coil, hence it induces an EMF in the secondary coil as well. Now, if the load is connected to the secondary winding, obviously there will be an EMF which drives the current through it. The magnitude of the output voltage then can be controlled by the ratio of the number of primary coil to the number of secondary coil. But the frequency of this mutually induced EMF is remaining same, that of the alternating source which is being supplied to the primary winding, right. As from this very diagram, right, the same principle, when I give the primary voltage to this primary winding, what used to happen? Because of this primary voltage being given and the nature of this primary voltage is alternating, the transformer works only for AC, does not work for DC, right. So, when we give an alternating supply to it, what will happen? An alternating current will flow through the transformer, right. So, I will be having a flux being produced according to the direction of the current being flowing in this, I will be having a flux being produced in the primary coil. The nature of that flux will also be alternating, right. This alternating flux, when links with the primary winding, because of I am having a flux rate of change of flux, so I will be having an induced EMF because of the Faraday's law. So, I will be having an induced EMF in the primary, say that is being given as E1. Similarly, as I am having a common core of the transformer, the same flux, it travels through the iron core and it links with the secondary winding. Once again the nature is alternating, that is not going to get changed. So, when this alternating flux or that links with the secondary coil, it will once again generate an EMF in the secondary coil. If at all I say it, it is as E2. So, in the secondary also I used to have an EMF being generated. This is what we call a mutual induction. The supply is only being given to the primary winding, but we are getting an induced EMF in the secondary winding as well, as the flux produced by the first one is linking with the secondary coil as well. Now, if at all I say the secondary circuit is completed, if the secondary circuit is connected with a load, with a kind of load, so this circuit is completed. In that case, obviously, I will be having a secondary current being flowing, right. So, this is how the transformer works. Now, what is the basic construction of a transformer, right? So, basically the transformer, you can see in the figure that the transformer, it consists of two inductive windings and a laminated steel core. The coils are insulated from each other as well as from the steel core. The transformer also consists of the container, right, for winding and core assembly, which is called as tank. Suitable bushings to take out the terminals which are being provided over here. These are the bushings, these are the terminals, oil conservator, right, oil conservator to provide the oil in the transformer tank for cooling purpose, right. In all types of transformers, the core is constructed by assembling or stacking the laminated sheets of steel with minimum air gap between them. Now, what is why this lamination is being done? Obviously, to reduce the eddy current losses, right. We will be discussing it later on, what are these eddy current losses and how these laminations reduces these eddy current losses, right. Now, the steel used is having a high silicon content and sometimes heat treated also so that the core can be provided a higher permeability and low hysteresis loss. Once again, this hysteresis loss needs to be minimized, and to minimize the hysteresis loss, which is based upon the area of the hysteresis curve. What is this hysteresis curve? This is the curve between B and H, right. We will once again be studying that, right, that is B and H curve. So, in that what we need is, we need to have a higher permeability material to be used, right. Now, the laminated sheets of steel are used to reduce eddy current, and the sheets are cut in the shapes of either E, I and L. To avoid the high reluctance at the joints, the laminations are stacked by alternating the sides of the joint. Now, coming to the classification of transformers, right, how the transformers can be classified. On the basis of the construction, the transformer can be classified into two types. One can be core type transformer, that is a general kind of transformer we see or we study, right, and the another kind is shell type. Now, what is this core type transformer? As it can be seen in the diagram itself, right. So, in the core type transformer, the windings are cylindrically wound. You can see here the windings are cylindrically wound, mounted on the core limbs, right. So, these vertical portions, what you can see over here, these vertical portions, these are being called as the limbs, whereas this horizontal portion, what you can see over here, these two horizontal portions, these are being called as the yoke part of the core, right. So, in this we used to have two limbs, it can be seen, the transformer used to have two limbs, and on these two limbs we used to have the cylindrical kind of winding being wound, right, in case of core type. That means the windings encircles the core, right, and that part or the portion of that core is not visible to us, it is not readily available for maintenance purpose, right, as the windings are upward, but the windings are readily available for the maintenance purpose because they require more maintenance. The core being made once, it is there, right, but the windings required maintenance and the windings are outward, right, air cooling. We can provide a better air cooling, the ventilation purpose, the ventilation provided can be a better one, right. Now, this is the property that the cylindrical coils have different layers and each layer is insulated from each other with the material like paper, cloth, mica, right? Low voltage windings are placed nearer to the core. Why? Because they are more easier, it becomes more easier for us to insulate them. So, how these cylindrical windings are being seen, you can see that initially we used to have the low voltage winding which is more nearer to the core, and then we used to have a high voltage winding, right. Similarly, half of the low voltage winding is being wound over here, half of the high voltage winding is being wound over here. Similarly, the next low voltage and half voltage windings are being, half of the low voltage and high voltage windings are being given over here with proper insulation in between, right. Now, similarly for a shell type, now you can see there is a very significant difference between a core type and a shell type. The very first thing, instead of 2 limbs, we used to have 3 limbs. In case of core type, if you just see, I used to have in just core type, if this is a core type transformer, right, in this I used to have just a single magnetic circuit, right. I will be having a single magnetic circuit in this. But in case of core, in case of shell type, if you just see, right, I am having 3 limbs, but the windings would be wound only on the central limb, right. That too, here the winding used to be a multi-layer disc type winding. It used to be a multi-layer disc type, right. And what do we understand by multi-layer disc type? Multi-layer disc type means it would be a sandwich kind of winding, used to have a small portion of low voltage winding, then a high voltage winding, low voltage winding, a high voltage winding. Once again, the low voltage winding, a high voltage winding would be sandwiched between 2 low voltage windings, right, so that it is properly insulated, right. It is having a double magnetic circuit. Why? Because you can see the windings are being wound on the central limb, right. So, the main flux would be produced in the central winding itself, right, and this flux would be divided into 2 magnetic circuits. One is this, 2 parallel magnetic circuits, right. So, the coils are former wound and mounted in layers tagged with insulation between them. A shell type transformer may have a simple rectangular or it may have a distributed form, right. So, these are the differences between core type and shell type. Coming to the differences being tabulated between the shell type and core type, if you just see, in case of shell type, the low voltage, high voltage windings are wound over the central limb and are interleaved, sandwich typed, whereas in case of core type, half of the low voltage winding is being placed over one limb and half over other, and the high voltage winding is placed first, low voltage winding is placed first over the core, right, and over it the high voltage winding is being placed on both the limbs, right. Now, the another difference is the flux in the central limb that divides equally and returns through the 2 outer legs. We have seen we are having 2 parallel paths in it, right, whereas in case of core type we have seen it used to have a single magnetic path. So, the flux has a single path around the yoke and the limb, right. Which kind of windings are we using? The third kind of difference, that is the interleaved or the sandwich coils are being used, whereas in case of core type we are using a concentric coils that are being used, right. The fourth point, obviously these are being preferred for low voltage, low power applications, right. I am having 2 coils, although I am having 2 limbs to wound, but here this will be preferred for low voltage, right, and in this case this is being preferred for high voltage, low current and higher power applications. Coming to the classification of transformer, but earlier what we have seen, the classification based on the construction, whether it is core type or shell type, right. But now on the basis of the purpose, right, whether you want to step up the voltage, whether the voltage needs to be stepped down, it can be of 2 types. One is the step up transformer, another one the step down transformer. A step up transformer, the voltage increases, right, with subsequent decrease in the current, where at secondary obviously, right. How would you define that which side of the transformer is acting as a primary and which side is acting as a secondary? In fact, a transformer is a bilateral device, right. The supply can be fed on both the sides, right. So the side to which you are giving the supply, you are feeding the supply, that side would be called as primary. And the side to which you are connecting your load, that side would be called as secondary. I can even change the sides to which I am giving the supply. That's why it is being called as bilateral device, right? Now, if at all I am saying it is a step up transformer, so obviously the voltage at the secondary, what you are getting is with an increased one, right? So with that, this I will be having a subsequent decrease in the current, because the power is at the both the sides, it's remaining almost same, right? Similarly, what is a step down transformer? So in this, the voltage decreases at the load side or at the secondary side with the subsequent increase in the current, right? Now, on the basis of the type of supply, I can once again have a classification of a transformer. What is that? One, I can be having a single phase transformer, I can be having a three phase transformer. The one what we are studying is the basic single phase transformer right now, okay. Now, on the basis of their uses, where they are being used, whether they are being used for a distribution purpose, whether they are using for a transmission purpose, right, or whether they are just being used for the isolation purposes, right, to just isolate two different circuits or for impedance matching, right. According to that, I can be having the transformers being classified as either power transformer, distribution transformer, instrument transformer. Likewise, power transformer, they are being used in the transmission networks where these are having a higher ratings, and basically step up transformers are only being used here, because that for the transmission purpose we all know that the generated voltage needs to be stepped up. The 11 kV or the 22 kV, which is being the generation voltage, 22 kV, that needs to be stepped up to a higher voltages, right. Likewise, in distribution transformer, obviously these are the transformer which are being used in the distribution network. Comparatively, the lower rating than that of the power transformers are used. That too, the transmitted voltages needs to be distributed, right. So once again, I need to get the step down transformers being applied over here, right. The transmission voltages are very higher, we know that 132 kV and all that. Those voltages needs to be stepped down up to which level, either 440 volts or 220 volts, right. So I need to have these distribution transformers. Instrument transformers, these are being used in relays and protection purposes in different instruments, right. Generally, the types of instrument transformer we used to have is the current transformer and the potential transformers. These two transformers are actually the sensing devices, right, the protection devices. They used to sense the change in the current or the change in the voltage, right, the current transformer. According to that, they used to operate the relay circuit, and thereby they used to operate the circuit breaker for protecting or isolating certain part of electrical network. Now, coming to a very important topic of the transformer, that is the EMF equation of the transformer, right. Now, we have seen till now that what is the working principle of the transformer. We have seen that in a transformer, when the source of an alternating current is applied to the primary winding, then due to this, the current in the primary winding, which we call it as magnetizing current also, that used to produce the alternating flux in the core of the transformer. Now, this alternating flux, it gets linked with the secondary winding. Because of this phenomena, what we call it as mutual induction, and EMF gets induced in the secondary winding, right. So, the magnitude of this induced EMF, that can be found by using the following EMF equation of the transformer. Now, we are going to let certain things. Likewise, say let N1, what is N1? N1 is the number of turns in the primary winding, okay. Now, what is N2? N2 is the number of turns in the secondary winding, okay. Phi m, what is phi m? That is the maximum core in the flux, maximum flux in the core, and what is the unit of the flux? That is Webers, right, and that can also be given as Bm into A. What is Bm? Bm is the maximum flux density multiplied by area. So obviously that is going to get me the maximum flux. Although we know that, why I am calling again a maximum flux, because I know the flux being produced in the transformer will be having an alternating nature, isn't it? As the supply is also alternating, so the flux produced is also alternating in it. So I will be having a maximum value being produced at pi by 2. right. So, that maximum value what it is attaining, the flux, that is being given as phi m. F is the frequency of the input of the AC voltage and the unit is hertz, right. As we can see, this is the alternating flux having the maximum value of phi m, right, and that is occurring at say by t by 4 time, right. Obviously, if the total time period is t, obviously in terms of t I know what's the relationship between the time and the frequency. So, the time period is just the reciprocal of the frequency, right. So, if at all I go with t by 4, that becomes 1 by 4f, right. So, now as shown in the figure, the flux rises sinusoidally to its maximum value, right, up to phi m from 0. From 0 to it rises to phi m. Now, it reaches to its maximum value in how much of a cycle? 1/4 of the cycle, that is in t by 4 seconds. That is what I told you. T by 4 seconds, where t is the total time period and of the sine wave, that is 1 upon f, and if at all I am saying that this is t by 4, so it has to be 1 by 4f, right. So, the average rate of change of flux, that is d phi by dt, right, that is d phi by dt, that has to be given. Rate of change of flux, how much is the flux is changing? Obviously, phi m minus 0, so that is phi m. And the time taken to change that flux from 0 to phi m, that was t by 4. If at all I substitute this t by 4 in terms of frequency, which we just find it off at 1 by 4f. So, that value would be phi m by 1 by 4f, right. So, the average rate of change of flux would be given by just 4f phi m. This is the average rate of change of flux, but this is the average EMF, right. So, the induced EMF per turn, that should be equal to the rate of change of flux per turn, right. So, the average EMF per turn, what we are calling, is 4f phi m. Now, we know that because we want to have the RMS value, right, it is the AC which is being induced, right. So, to have the RMS value, the factor has to be introduced. Which factor? The factor which is relating the RMS value and the average value. We know that factor has to be the form factor, Kf. And how we define this form factor, right? We have already seen that in our second unit. This form factor is defined as the RMS value of an alternating quantity to the average value of the alternating quantity, of that same alternating quantity, right. And for a sinusoidal wave, if at all we just calculate, so RMS value is how much? 70.7% or 0.707 of the maximum value, right. And the average value used to be 0.367 of the maximum value. So, this value we used to get it as 1.11, right. So, the form factor used to be 1.11, right. So, I will just multiply to have this RMS value. What I am going to do? I am going to multiply it with the average value. So, just multiplying 1.11 factor with the average EMF per turn, we can have the RMS value of the EMF per turn. So, the RMS value of the EMF per turn would be given by 1.11 multiplied by 4f phi m. That will be given by 4.44 f phi m, right. So, the RMS value, this is the generalized equation, right. Now, this is per turn, that means for single turn, right. So, the RMS value of the induced EMF in the whole primary winding, what we termed it as E1, right. What is E1? That is the RMS value of the EMF per turn, that is the RMS value of the EMF induced in the primary winding. And how many turns does it have? The primary winding used to have how many turns? N1. We just described it in the earlier slide. So, obviously, E1, which is nothing but the RMS value of the EMF induced in the primary winding, would be given as 4.44 f N1 into phi m. The number of turns in the primary, that would be multiplied to it. Similarly, the RMS induced EMF in the secondary winding, it is having N2 number of turns. So, it will be having E2 is equals to 4.44 f N2 phi m. So these two equations gives me the EMF equation of the transformer, or the generalized equation that can be just given by E is equals to 4.44 F phi m n, where N1 is the number of turns in the primary and N2 is the number of turns in the secondary. Now just continuing on with the EMF equation, right. Now we have seen both the EMF equation of the primary and the secondary. Now going for the ratios of the transformer, if you would just see from the EMF equation of the primary and secondary, the voltages of the transformer, and now taking the ratios of these equations, if I just do E2 by E1, right. So what we got the EMF equation as? We got it as, if at all I just say E2, that is equals to 4.44 F phi m N2, right, and even we got it as 4.44 F phi m N1, right. If at all I take the ratios of these two, if you just see, I can be very much conclusively can say that this E2 upon E1, this is what we used to call it as voltage ratio, and that must be equals to, all of the things would be striked off and I will be having just N2 by N1. This N2 by N1 is what we are calling it as turns ratio. E2 by E1, N2 by N1, we used to call it as turns ratio, which is nothing but the secondary number of turns to, it is the ratio of the secondary number of turns to the primary number of turns. Similarly, I can even give this as V2 by V1. What is V2? V2 is the terminal voltage what is occurring across the load, right, and V1 it is the supplied voltage, right, and we know that the E2 is almost equal to V2, E1 is almost equal to V1, so I may even take V2 by V1. That is equals to the voltage ratio that can be given over here, V2 by V1. I also know that in a transformer, the power is remaining same. That means the primary power, that is V1 I1, must be equals to V2 I2. If that is the case, if at all I take V2 by V1, that must be equals to I1 by I2. So I may add one more ratio over here, this V2 by V1, which you call it as voltage ratio, that must be equals to I1 by I2, the reverse, and I call that as current ratio. And combiningly all these, that means combiningly all these, means combiningly E2 by E1, which is equals to V2 by V1, which is equals to I1 by I2 equals to N2 by N1. I may call it as K. And what is this K? This K gives me the transformation ratio of the transformer by which the voltages has been transformed or the currents has been transformed, right. I suppose this is just all for today's class. So in the next lecture, we'll continue on with the ideal transformer. Thank you all.